Welcome to part three of the discussions regarding minerals. In parts one and two, we covered the basic chemical principles that I think are appropriate and will help one understand and appreciate what a mineral is. In part one, we looked at the atomic characteristics, the atom. We looked at the periodic table. In part two, we looked at different kinds of bondings in terms of how minerals or how elements bond together to create minerals. So, for the remainder of the mineral discussion, we are now going to talk strictly and solely about minerals and apply some of our chemical principles that we learned in both parts one and two. And so to begin with, this first slide asks the question, what are minerals? And I'm going to put a series of objects on the screen, and you're going to decide if that object is a mineral or if the object is not a mineral. So we have some gold. There's some gasoline there at the lower part of your screen, a diamond, liquid water, and a piece of wood. And and a piece of wood. So we need to decide then which of the following objects, gold, gasoline, diamond, water, or wood, is in fact a mineral. In order to determine if the gold and the diamond are considered minerals, and the rest of the objects in the previous slide, we need to look at this definition of a mineral. And I like to call it the 5-part mineral definition. Typically, you can read in a geology textbook or you can read in an earth science book and so forth. And the definition will be written in paragraph form and so forth. And what I did, or what I like to do, is again put it into a bullet point or a 5-part definition. So to be a mineral, to qualify as a mineral, the mineral has to be what we call naturally occurring. And naturally occurring means that it's not man-made. Humans did not put the chemistry together to form the minerals. In fact, it was conditions on Earth that put the elements and chemistry together and to form these particular types of minerals. So they are all natural occurring. To be a mineral, it has to be inorganic, which means non-living. And so the type of science or mineral science that we look at for minerals is physical science or physical chemistry, not organic chemistry. So organic chemistry deals with living things. Physical chemistry deals with non-living type substances, in this case, minerals. To be a mineral, it has to be homogeneous and it has to be a solid. So if your substance is either a liquid or a gas, it would not by definition be considered a mineral. Homogeneous, meaning that it's pretty uniformed throughout. And so the chemistry of that particular substance, is the same. And that what homogeneous means, the same throughout. To be a mineral, it has to have what we call a definite chemical composition. And when we say definite chemical composition, we're really referring to, for example, if we look at a chemical formula that says Fe2 with an oxygen atom on there. That means in order to be stable, you have to have 2 iron atoms to every 1 oxygen atom. And so we would say that that would be a definite chemical composition. So the ratios of elements that come together have to be stable. So in this case, Fe2O is a stable content or compound. And the last part to make a 5-part definition of the mineral would be that it has a definite crystalline internal structure. And this means that in order to be a mineral, it has to have some type of orderly pattern of atoms that arrange themselves in a definite what we call crystal lattice. And we looked earlier at some of the pictures of elements, and you noticed that there was an orderly pair of atoms that combined together, some internal geometry associated with it. So to be a mineral, it's got to have that internal structure. So it has to be naturally occurring, inorganic, homogeneous, definite chemical composition, and definite crystalline internal structure. So by definition, there are about 4,000 different minerals that have been defined and found on Earth that fits this 5-part definition. Of those 4,000 different minerals, there are about 25 common minerals that combine together to form rocks. So you can see that there's a lot of moderately to rare type minerals that exist on the Earth's surface and interior parts of the Earth as well. But 25 of those are just common to form rocks. So we go back to our objects and we ask the question, is a tree a mineral? And the answer would be no, not by the definition, because a tree is definitely living and a tree is definitely organic. How about liquid water, for example? Would that be considered a mineral? And the answer to that would be no, because again, minerals have to be solid. And of course, liquid water is not solid, it's a liquid, therefore it would not qualify as a mineral. But what about ice? Let's look at the substance ice. Is that a mineral? And the answer to that would be yes. In fact, let's see if ice fits that 5-part definition. So ice, does it naturally occur? The answer is yes. Does ice inorganic, non-living? The answer is yes. Does ice occur as a solid, homogeneous solid, same chemistry throughout? The answer is yes. Does ice have a definite chemical composition? Yes, H2O, 2 hydrogens to every oxygen. Does ice have a definite crystalline internal structure? And the answer to that is absolutely yes. In fact, I would invite you to get on your Google and look up images and look up snowflakes. And if you look at electron scanning microscope pictures of snowflakes, you find that ice can form various types of crystalline type structures. And in fact, it can be quite beautiful. So in fact, ice is a mineral. It fits the 5-part definition. So we're going to spend, for the remainder of the discussion of minerals, we're going to spend most of our time in the latter part of the definition. We're going to spend most of our time looking at the internal structure and the orderly arrangement of atoms within a mineral. So to start with, we ask the question, what's inside a mineral? A mineral's crystalline structure, then, its internal geometric shape, is really the result of how the atomic arrangement or how the atoms align themselves. And we're going to find that atoms come in different sizes. And so the internal arrangement of how the atoms arrange themselves is really dependent on the size of various combining ions and also how the ions bond together in terms of what kind of bond is there. The example I have is at the lower part of your screen. We look at a sodium. We look at sodium chloride. We look at a salt crystal, and basically what we see a sodium atom, and it's combining with a chlorine atom. And because of the sizes, because of the fact that the chlorine or the anion is much larger than the sodium atom, which is the cation, it arranges itself by geometry into cubes. And certainly when you ever look at a piece of salt under a microscope, at least that's what I did when I was a kid, you see many, many little cubic type structures, which is again indicating that the sodium and chlorine are aligning themselves, creating this internal structure. So do all minerals grow and show the observer their crystalline shape? In other words, remember, to be a mineral, it has to have a definite crystalline structure. And many cases, if you're out in the field, you're looking at minerals, you pick up a sample of a mineral, it really doesn't show its crystalline structure. So for example, here is where we have a mineral of pyrite, and it's 2 irons and a sulfur, so 2 irons and 1 sulfur combined together. And given the conditions, if the conditions are correct in nature, that iron and sulfur will line itself to produce a perfect cube. And you can see in my picture here that this is a perfect cube created by nature. In fact, if you were to measure that angle between this cube, it would be exactly 90 degrees. Wouldn't be 89.9 or 90.2. It'd be 90-degree angles, and that's how special nature is. Nature can allow that to happen. But normally you would find a pyrite that looks more like this in the field. And so you go to an area where a pyrite has been concentrated and deposited, and you would see just maybe some half cubes or three-quarter cubes and so forth. And that's typically how you would find it in nature. Or look at this picture here in the lower part of your screen. This is an electron scanning microscopic picture of quartz, which is the combination of silicon and oxygen. So there's your cation and your anion that have combined together. And typically quartz will form what we call hexagonal crystal structures. And if you look at the quartz, you can basically count 6 sides. 1, 2, 3, 4, 5, 6. And what's unique about this picture, and it's one of my favorite pictures, this is an electron scanning microscope picture, meaning that it's very, 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 very small. It's almost down to the atomic level, and yet it's forming the internal structure even at the atomic level. And so again, you can kind of see that hexagonal crystal habit that quartz takes on when Si, silicon, oxygen combine. Here then is an actual hand specimen of a quartz crystal. And if you look closely, you should see the fact that the hand specimen looks exactly just like the electron scanning microscope picture. So the point here is that when you're looking at a crystal and you're looking at the crystalline structure, the actual crystal faces that are formed, you're really looking at the atoms. You're really looking at how the atoms have combined together to produce that internal structure, which I think is just fascinating that nature can do this. So if you want to know what a mineral looks like at its atomic level, it looks just like the hand specimen. If you can find a mineral that's displaying its internal structure. Do we normally find quartz, for example, out in the field that looks like this picture where my arrow is? Normally we find quartz that looks like this. So the question is, why in the field then, in most cases, do we not find minerals that are displaying their beautiful internal structure? And the answer to that is that in nature, there must be 3 conditions that must exist to allow the chemistry to come together and bond and form the internal crystalline structure. So 3 conditions must exist. If one of these conditions are missing in nature, then you're not going to see the nice, beautiful crystal structure formed by the internal structure. And so you have to have time to grow. So in order for minerals to take their internal structure, the solutions have to have time to build and time to grow. You must have enough space. In most cases in nature, there's not enough space for minerals to begin to grow and produce their internal structure. And then the last condition must be enough materials. So again, in order to show the internal structure in hand specimen, where one can see conditions must be time to grow, enough space, and enough materials. And if one of these conditions are missing in nature, you're not going to see those nice internal structures. In fact, looking at these 3 conditions, growing, space, and materials, which condition do you think is common that is missing from nature? And probably what's more missing is space. And later on, we're going to look at igneous rocks, and you're going to see where some igneous rocks shows mineral texture, some igneous rocks do not. And it's very related to the fact that there's either space or no space. And so space is usually the common condition that's missing. This next slide is a really interesting slide. And this slide shows shows an area in Chihuahua Desert, Mexico, called Crystal of the Caves. And if you were to type in Crystal of the Caves on YouTube, there's a documentary that kind of talks about what's going on in this slide. And basically, in this area of Mexico, folks were drilling, I believe it was for groundwater, and as they were drilling down through the surface of the earth, they got 150 feet below the surface and actually encountered a huge cavern. And once they learned that there was a cavern located down there, they structured it where folks can go down and be inside that cavern and take a look. And what they found was a huge area in which there were some enormous size gypsum crystals that are formed. And what you're looking at in the slide here are crystals that are gypsum, which is actually a very common, what we call evaporite mineral. It's a calcium sulfate mineral, and very common on the Earth's surface. But here it is existing 150 feet below the Earth's surface in this cavern. And you can see by looking at the picture that, these size of these crystals are huge. I mean, they're larger than an average human being, for example. And in this documentation of Crystal of the Caves, they were so intrigued by this discovery that they allowed every ologist you can think of to go down there and inspect it and take a look. So mineralogists, geologists, biologists, any ologist you can think of. And the temperatures were so hot that in many cases they had to wear different kinds of clothing, to keep themselves cooler. And from my understanding, folks can only be staying down there for 10 minutes or so. But in any event, the question is, why do these gypsum crystals 150 feet below the Earth's surface exist? What conditions must have been evident at that depth to be able to let these large crystals form? And you got it. It would be enough space, time, and solution. And interesting enough, when they discovered this cavern of these beautiful gypsum crystals, to get down there, they had to eliminate or take out the solution, because these were all saturated, in a type of in solution. And once the solution was taken out, the gypsum crystals quickly began to disintegrate and decompose, because now we're missing one of the components. And so, from my understanding, the solution was put back into the cavern and sealed up, and now it's forever protected. So this is, again, a very good example of enough space, time, and solution. This next slide, again, refers to the internal structure of how the atoms align themselves to produce different types of crystal structures, and in this case, crystal faces. A crystal face is defined as a very smooth surface along the crystal. So where my arrow is kind of going around the perimeter, this would be defined as a crystal face. There's a crystal face. There's a crystal face. And what was discovered is that these are quartz crystals, and the angle between the crystal faces, so this real red arrow here, this red line, indicates the angle. So one can measure the angle between the crystal face, and that angle is always consistent with what type of mineral you're looking at. In this case, it's quartz, and no matter how large the mineral is, in terms of, it could be quartz, but no matter how large, small, tiny the mineral is, it'll always display the same angle between the crystal faces. And that's owed directly to the fact on how the little atoms line up or align themselves within the mineral, making that internal structure. So again, no matter how big that quartz is or how small it is, the angle between crystal faces will always be the same. And that's what this slide is showing you here. That's the angle between the crystal face. So this was discovered by a Danish physician named Nicholas Steno in the mid-1600s, in 1669, it says on the slide. And Steno discovered that the angle between crystal faces on various kinds of minerals are always consistent. And in fact, he wrote, if you look at the top of your screen, this is known as Steno's law, and it states the angle between any corresponding pairs of crystal faces of a given mineral is constant, no matter what the overall shape or size of the crystal might be. And really, what this means is that consistency between the angles reflects the internal atomic arrangement of atoms. And why is this important? Because back during the 1600s, 1700s, and maybe even today, a lot of folks believe that minerals have mystical and magical powers. Because you have to admit, when you find a mineral in nature in which there was enough space, time, and solution, and it presents its crystalline faces, it's a very beautiful natural substance. And so a lot of folks, certainly in the 1600s, 1700s, believed that these minerals had powers. And what Steno indicated is showed that, you know what, they really don't have magical powers. It's just a result of atoms aligning themselves together and producing these consistent angles. So basically, it was a little bit of science applied to a mystery. But even today, folks believe that minerals have special powers. And who am I to say? Maybe they do. I don't know. So when we look at the growth of a typical mineral, we look at basically a mineral grows based on an atom by atom crystal growth. And again, based on the size and how the atom bonds together, based on the size of the atom and how the atom bonds together, is going to dictate that internal structure. So in this case, I have a couple of graphical examples. Here I show in which the atoms line up as cubes. And so now we get one cube stacking on another cube, and so forth. And then as that mineral grows, it produces a cubic structure, for example. Here in the second example, where my arrow is, here we have hexagonal crystal growth. And here you could count 6 sides. And again, it's all dependent on the size of the atom and how the atom bonds. And here is what we would call a rhombohedral type growth, in which you have basically little parallelograms, not quite cubes, that have now formed together. So again, based on that size of the atoms and how they bond, the mineral will form different types of internal structures. On the lower part of the slide that you see is just some more examples of some real beautiful quartz crystals that had enough time, space, and solution. But again, you can have skinny, tall, short, fat type crystals, and the angle and the atom by atom growth will always be the same. So let's shift gears a little bit and let's look at the atomic arrangement of atoms in a liquid, for example. And when we say a liquid, you're probably envisioning water or liquid that moves. But in fact, you can have a liquid that moves very, very, very slow and appear as a solid. So it can be really looked at as a liquid solid. So we look at the atomic arrangement of atoms in a liquid solid, so a solid or a liquid that moves very, very slowly. And really, when you look at that arrangement, there is none. Atoms are randomly arranged, and they don't display any kind of order or crystalline structure, as we discussed in the previous slides. So when we have a material that's solid but behaves as a liquid without an arrangement of atoms, we refer to this as an amorphous solid. So an amorphous solid is a liquid type solid then that possesses no internal structure. So let me repeat that. An amorphous solid is a type of material that displays a material that does not possess an internal structure. And so that is a special kind of mineral because it lacks that last part of the mineral definition, and we refer to those as mineraloids. So a mineraloid is a type of material that is an amorphous solid. It lacks that internal structure. So how do you know if it's amorphous? Well, one of the ways one can determine an amorphous solid is the fact that it has no melting point, meaning that when you begin to add heat to an amorphous solid and you begin to heat it up, it never really melts. It never really moves from the solid phase to the liquid phase. But in fact, where it does, it moves more into, and I'm going to use a non-scientific word here, moves into a gooey phase, or maybe behaves like hot taffy. And a really good example of that would be glass. What happens when you heat glass? When you heat glass, it really doesn't melt into a liquid, but instead it gets very gooey. And in fact, people who shape vases and glass blowing type folks depend on that behavior, depend on that amorphous nature of glass. Plastic is another amorphous type material. Wax would be considered amorphous. And so when you look at an internal structure, that's amorphous, you may observe something like this at the atomic level. So here you see a series of atoms that are all bonded and combined together, but very randomly arranged. That would be something that's amorphous. If you contrast that and look at a crystalline structure, so in this part of the slide, we have an amorphous structure here in which the atoms are arranged very randomly. And if you contrast that to a crystalline structure, the atoms have a definite geometrical order. And that distinguishes the difference between a crystalline material here and then an amorphous material here. And so getting back to the melting point of an amorphous structure versus a crystalline structure, when you add heat to a crystalline structure, there is a predictable temperature at which the bonds between the atoms will break and will move from a solid right into a liquid. And again, if you go back to the amorphous structure, applying heat, bonds really don't break. They just start moving around and it becomes a lot more mobile, hence gooey, and that would typically indicate an amorphous structure. And just in case you didn't know, on the right bottom side of your slide, there's wax, glass, and plastic. So this brings us now to looking at mineral families. And so scientists have identified approximately 4,000 different minerals, as we kind of indicated at the beginning of the discussion of this part. And so we're going to ask ourselves, what's then in a rock? Because the next few slides, we're going to start moving into the discussion of rocks. Because remember, minerals make rocks. So what's in a rock? And so I've listed here common elements that make up rocks. And so we have 8 elements making up rock-forming minerals. And if we start with the bottom, we can look at, so go to the bottom part of your slide. And we have less than 1% of the Earth's crust. So these are elements that make up minerals on the Earth's crust. Let me repeat that. These are elements that make up the rock-forming minerals on the Earth's crust. And so less than 1% would be Ti, titanium, hydrogen, manganese, and phosphorus. Then you see that potassium, 1.68%, sodium, and then magnesium, calcium at 5.06%, iron, 5.8%, aluminum makes up 8% of the elements that make up rock-forming minerals on the Earth's crust. Now, these percentages are percentages what we call by weight, meaning if you could take a sample of the Earth's crust and weigh the sample of the Earth's crust, what would come out of that would be these, you'd have a little bit of potassium, 1.68%, and then 8% of that sample would more likely be made up of aluminum. Now, look at the next 2 elements, and this would be oxygen and silica. And if you notice, oxygen and silica by far make up the dominant portion of elements that make up rock forming minerals. And in fact, oxygen is the largest. Oxygen is 45.2%. Silicon is 27.0%. So again, oxygen and silica by far. Be prepared on the exam that you will be asked what is the most dominant element on the Earth's crust. Now, let me repeat that question. What is the most dominant element on the Earth's crust? And your answer, of course, would be oxygen. Now, if we consider the entire Earth, so here we would consider the core, the mantle, and the crust, and we look at the most dominant element on the entire Earth, again, including the entire Earth and the interior, it would by far be iron. So iron is by far the most dominant element on Earth, but the Earth's crust, by far, it's going to be oxygen. So based on the elements that make up the different types of rocks, we can now separate minerals into their what we call mineral classes. And to separate the mineral in their particular classes, it's based on the anion complex. So here we go. We're going to revisit these terms, cation and anion. And remember that cation are positive ions, which is typically the metals, and the anion is typically the non-metal. So when we look at mineral classes, it's based on the non-metal or based on the anion complex. And so my example, using sodium chloride, we would say that sodium represents the cation and chlorine represents the anion. So in this case, halite or sodium chloride then would be classified or categorized in the what we call group 17 of the periodic table, where chlorine exists. So this is known as the halides, but again, it's based on the anion. So the mineral groups, according to the anion, I think we got about 7 of them. So we've got the oxides, the sulfides, the sulfates. We've got the native elements, the halides, the carbonates, and we got the silicates. And so again, each one of these mineral groups are where minerals are grouped according to the anion or according to the nonmetal. And for example, I want you to look at this group: oxides, sulfides, sulfates, native elements, halides, carbonates, and silicates. And based on what you've just learned in the previous slide, in terms of what the dominant elements on the Earth's crust are, what group of elements would represent, what group of minerals would represent the largest group of minerals based on these mineral groups and based on silica and oxygen being the dominant elements on the crust. So most students will say oxides because they see the oxygen right off the bat. And in fact, the real answer is silicates. And you'll see a silica and you'll see an oxygen. So we would say, so silica and oxygen right down here. So we would say then that the silicate group by far is the most dominant mineral group on the Earth's surface because it both has silica and it both has oxygen. So let's take a look now at the silicate group, or let's take a look at the two elements that combine together to produce that most abundant mineral group, the silicates. And so there's Si, silica, and oxygen. And with the combination of silica and oxygen, again, makes the silicate mineral group. This represents the largest mineral group. We take the silica and we take the oxygen, we combine it, and we make the ion silica tetrahedra. And what to notice here is this little -4. And in chemistry, that little -4 gives you the ionic state of the silica tetrahedron. And the higher that number, in this case it's -4, which would be high, is telling you that this particular ion then is very highly unstable. And in fact, it's unstable it wants to combine with any kind of metal that it sees. So if a calcium or a sodium or any kind of the common metals, cations that we looked at earlier come along, the silicate tetrahedron, the SiO4, will attach itself to that and produce a mineral within the silicate tetrahedron, within the silicate mineral group. So the tetrahedron is covalently bonded, meaning that this is very, very, very strong ion. Covalently bonded, meaning that the electrons are being shared, 4 oxygens with 1 silicon. The tetrahedron forms the building block for all silicate minerals. Very strong, hard to break, again, unstable. And so what I did here is, if you look at a picture or a diagram that illustrates the silica tetrahedron, which we saw earlier in part 1 of the discussion, you see that you've got the silica atom in the center, surrounded by 4 oxygens, again, all covalently bonded. And if you were to draw the geometrical structure produced with this covalent bond, you would find that it really is a series of pyramids or triangles that are bonded together, forming a pyramid. And if you think back to the time where I believe most of you folks have had some type of geometry course, maybe at the high school level, and what did you learn about the triangle? And you should have learned the triangle is a very rigid, strong geometrical shape. And by combining 3 of them in nature with covalent bonding, you find that this tetrahedron is very, very strong. And minerals that belong to the silicate family of minerals will easily scratch glass. So, for example, quartz is a silicate mineral composed of silica and oxygen, and it easily will scratch glass because of its covalently bonded characteristic. So this last slide within our part 3 of minerals is how do silicate tetrahedrons bond together? And this slide is a little bit of an introduction to rocks, which will be coming up in the next discussion. And really, different silicate structures or tetrahedrons is really a function of temperature. And we're going to go through a temperature curve, and I'm going to show you how the silica tetrahedron rearranges itself as a function of temperature to form various and different kinds of silicate minerals. So what we have here is where my arrow is what we call a silica tetrahedron. So this is your typical silica tetrahedron, and I purposely have drawn it in a triangle fashion because that indicates the structure of the tetrahedron. And then here we have a temperature curve. And what we're going to learn when we start looking at rocks and start looking at igneous rocks, that temperatures in which to make all of the elements, the common elements that we learned in the previous slides in this discussion, liquid, we have to have temperatures at least in 2000 degree, 2200 degree Fahrenheit range. And when rocks are melted to 2000 degrees, we produce magma. And magma has all of the common elements that we talked about earlier. And as we cool that magma down, as the magma cools slowly and slower and slower, then the silica tetrahedrons will rearrange themselves into a particular crystalline structure dependent on that temperature. And so again, what this curve shows you is that here we have magma at 2000 degrees, and now we're cooling it. It gets cooler and cooler, and finally we get cooler to the point where we get down to the last part of the curve, and that's when the magma is completely solidified. And what I want to show you here is how the silica tetrahedron, again, rearranges itself as a function of temperature. So let's start by lowering the magma from maybe 2000 degrees to about 1800 degrees. And at that point, what begins to happen is you have your silica and oxygen that has been floating around inside the magma. And now it begins to combine with magnesium, which is a cation. So there's your cation, there's your anion, and now it produces a single, what we call single type tetrahedron structure, which is a mineral we call olivine. So we would say then that olivine mineral is the first mineral to precipitate or become a solid born from this magma liquid. If we lower the temperatures a little bit lower, and then once we lower the temperatures a little bit lower, then we start rearranging the tetrahedron. So you can see that the tetrahedra has been rearranged now into what we call a hexagonal ring. And here we have beryllium, aluminum, and then there's the Si, silica, and oxygen rearranging itself into a mineral called beryl, which in fact, given enough space, time, and solution, if you find beryl, that's usually classified as an emerald. A green emerald is what you would find as a mineral. We lower the temperatures a little bit more, and now you can see the configuration of tetrahedra begin to rearrange themselves according to a new temperature. And now we start to produce what we call single chain tetrahedra. And now it joins up with calcium and magnesium. So there's two additional cations, and we form a mineral group called pyroxene group, which now has a different internal structure. Again, we continue to lower the temperature of the magma some more, and now we begin to rearrange, or nature begins to rearrange the tetrahedra, and now this is rearranged into what we call double chain tetrahedra, and we have calcium, magnesium, and there's the silica in a different ratio, and this is known as the amphibole group of minerals. So again, because of temperature, that tetrahedra now is rearranged according to its temperature. We lower the temperature some more, and now we form what we call the mica group, or we form minerals that take on what we call a sheet structure. And you can see the very long chemical formula for the sheet structure. Here we have combinations of potassium, magnesium, iron, and aluminum and silica. So there's our silicate right here, and a little hydroxide on the end of this. And this forms the mica group. And what's interesting about the mica group is now this particular mineral you can actually tear off in little sheets. And as you tear off it, little sheets, it breaks along these ionic bonds. And then finally, we're getting down to a point where the magma is just about completely cooled. It's almost cooled into a complete rock. There's still some liquid remaining, and we're talking probably around 600 degrees Fahrenheit. And finally, once it completely cools, we end up forming what we call a framework tetrahedron, which is composed of the leftover silica and oxygen that remains in the magma, because all the other cations have been used up, and now finally also left is silica and oxygen, and this forms that framework, which is dominantly going to be the mineral quartz. And so again, this is a great introduction to looking at the different internal structures of silicate minerals, because every silicate mineral has a different structure according to when it formed. And this is a good introduction to igneous rocks that we will be looking at here in the next discussion. Now, for test purposes, it's going to be very important that every student learn the different chemical formulas and the names of each one of the internal structures for each one of the silicate minerals. So you need to learn what a hexagonal ring is in terms of its chemical formula and so forth. No, not really. So right now you're probably having relief. I am not expecting students to learn the double chain, single chain type of silicates. Now, if you take a mineralogy class, you would actually learn that. But for this level of the class, the question you're going to be asked and be responsible for is, for example, why on Earth, in nature, are there different types of silicate minerals? In other words, why are there different silicate minerals with different structure? And the very simple answer is is a function of lowering temperatures of a magma. So let me repeat that. The question is, why are there various types of silicate minerals found on the Earth's surface? The answer is because it's a direct result of lowering temperatures of magma. And so that's what you should focus on and understand and comprehend for the exam.